Welcome, Nocturnal Minds, aboard. Your learning journey starts now. So, picking up from our discussion on scientific measurement and mechanism explanation, we naturally arrive at the tools scientists use to understand these mechanisms, models. Now, the word model itself is a bit of a slippery fish, isn't it? You hear it used everywhere, but trying to nail down one single perfect definition. Good luck with that. It's like trying to define art. Everyone has an opinion, and they're all different. But maybe, just maybe, instead of chasing that elusive definition, we can look at what models do. What stands out is their connection to representation. A model, almost by definition, is meant to stand in for something else, a real building, a hypothetical scenario, a physical system. Think about a model of a bridge. It's not the actual bridge, is it? It's a simplified version, focusing on certain aspects, like the load-bearing structure, while ignoring others, like the paint color or the traffic flow. That's the key. Models are representations, often abstract and idealized ones. Now, scientists aren't shy about using different kinds of models. We've got the classic physical scale models, like those intricate plastic replicas of DNA you might see in a museum. These are iconic models. They visually represent the target system, showing its features and relationships in a tangible way. Then there are analogical models. Here, the idea is that two things are similar enough in some crucial aspect that understanding one helps us understand the other. The classic example is using billiard balls to model gas molecules colliding in a container. The motion and interactions are analogous. And finally, we have mathematical or abstract models. These are the heavy hitters, often expressed through equations and formal logic. Think of the simple harmonic oscillator, a mass on a spring, which is a mathematical model representing many physical systems. Despite their differences, all these types share a core function, representation. And what guides this process of representation? Idealization and abstraction. We strip away the messy details to focus on the essential structure. Okay, so we've got these different flavors of models. But if I had to pick one that really grabs the attention of both philosophers and physicists, it would be the mathematical model. Why? Well, first off, they often have this global reach. Unlike a specific scale model of a particular bridge, a mathematical model like Newton's laws can apply to countless different situations involving forces and motion. They're deeply intertwined with the grand theories of physics. Second, they're incredibly powerful for making predictions about how systems change over time. If you know the state of a system now, a good mathematical model can tell you what it will be like later. And third, let's be honest, math is the lingua franca of science. When scientists talk about the world in precise terms, it's usually through mathematics. So, no wonder both philosophers dissecting the philosophy of science and physicists doing the actual work spend a lot of time thinking about these mathematical constructs. That's where we're heading next. And it's not just philosophers who geek out over mathematical models. Physicists themselves often see other kinds of models, like those physical scale models or even analogies, as helpful aids, maybe ways to get intuition, but not the main event. The real action, the central part of their work, is constructing and manipulating mathematical models. In fact, when physicists step back and think about their own methods, they often draw a useful distinction between two types of mathematical models. On one hand, you have theory-driven models. These feel like they come straight out of the theoretical framework. You take the core principles, add some specific assumptions for the problem at hand, and boom, you get a model. It seems almost like a logical consequence of the theory. Then there are phenomenological models. These are built differently. They often rely on experimental results, maybe some educated guesses, or concepts that aren't directly tied to the deepest theoretical foundations. The key difference from the physicist view is that these phenomenological models don't seem to follow directly from the theory in the same deductive way. This distinction gives us a fascinating glimpse into how models are actually built in practice. Now, let's shift gears to the philosophers. For a long time, a big goal was to find a unified way to understand both scientific theories and models. How are they related? What's the underlying logic? Two major schools of thought emerged. First, there's the received view, or are we. Think of this as the old-school formalist approach. It sees scientific theories primarily as sets of axioms and rules, like a mathematical proof system. Models in this view are more like the structures that satisfy parts of those proofs. The actual representation of the physical world is done by the sentences of the theory, not the models themselves. Models are kind of secondary, helping us understand the formal system. Then came the semantic view, or SV. This is a big shift. It says, hold on, let's give models some respect. According to SV, a scientific theory isn't just a set of sentences. It's fundamentally defined by the class of possible models it describes. Think of a theory of gravity not just as equations, but as the set of all possible space-time geometries compatible with it. Here, models are seen as having their own direct power to represent reality, standing shoulder to shoulder with the theory itself. The received view, with its focus on syntax and formal logic, ran into some serious trouble. Critics pointed out that it forced awkward distinctions, like separating observational terms from theoretical ones, which seemed impossible in practice. It also relied on vague notions of correspondence rules to connect the formal symbols back to the real world. But the biggest blow, especially for our purposes, was that it basically denied models any real role in representing physical reality. That's where the semantic view steps in. SV flips the script. It says, models are the stars here. A theory is essentially the collection of all possible model types it could generate. Whether defined using the math of the theory itself or via set theory, the focus shifts to the models. This was a huge deal because it was the first major attempt to systematically analyze what mathematical models are and how they work in science. It really highlighted their importance as guides to understanding the world. So, under the semantic view, how does this play out? We get these theoretical models, which are directly tied to the formal structure of the scientific theory. The idea is that these models are proposed specifically to represent some target physical system out there in the world. Now, remember those experimental data we talked about earlier? Philosophers like Supps suggested building data models directly from that raw measurement data. The core idea of SV is then to compare these two, the theoretical model derived from the theory, and the data model built from observations. Since both are mathematical structures, the comparison involves mapping the elements and relationships of one onto the other. This mapping, according to SV, is supposed to capture the entire relationship between theory and experiment. Now, different proponents of SV have slightly different takes on what this mapping means. Van Fresen talks about isomorphism, a perfect match. Da Costa and French suggest partial isomorphism, a match in some respects. Supp interprets it more counterfactually, as the model being an idealized replica. And Geer suggests it's about similarity in degrees and respects. But the common thread is this structural mapping. This sounds neat, right? Theory models map to data models. Voila, we understand the theory-experiment link. But here's the rub. What if this mapping relation is the only way a model can be considered representational? Then, any scientific model we actually use would either have to be identical to a theoretical model or somehow reduced to it. Does that sound right? Enter philosopher Margaret Morrison, who raises a crucial objection. She points out that in real life, science rarely operates with such a clean split between purely theoretical models and data models. Scientists don't just sit there checking if their fancy theoretical model maps perfectly onto the data model. Morrison argues that the semantic view, while insightful, might be more of a rational reconstruction, a nice logical formulation, rather than a description of how science actually works. Her bigger point is that theories themselves are often too abstract and idealized. They tell us about general principles, but not necessarily the specific mechanisms at play in a particular system. For that, she says, we need scientific models, especially the phenomenological ones, acting as independent mediators explaining the nuts and bolts of how things work. So Morrison offers a different lens. Representational capacity should be judged by explanatory power. A model represents something well if it successfully explains what happens in the physical system. This criterion, she argues, works for both kinds of models. Theory-driven models explain because they're linked to the theory, sure. But phenomenological models also explain, even if they don't have that direct deductive link. The SV struggles here because it tends to downplay the representational value of phenomenological models precisely because they don't fit neatly into the theoretical model structure. Morison's approach flips this. Instead of defining representation as a primitive property based on structure, she asks why a model is representational. Her answer is, because it has explanatory power. This becomes a necessary condition for being a representational model. It's not just about the structure, it's about the function of explaining the phenomena. Let's make this concrete with an example. Imagine a vibrating string, like on a guitar. We want to model it. We make some simplifying assumptions. The usual suspects. Supports are rigid. The pluck is tiny. Tension stays constant. Based on these, we can use the classic wave equation. This model does a great job explaining the transverse waves, the up and down vibrations. But what if we attach a force meter to measure the tension along the string? The wave equation, with its constant tension assumption, doesn't explain the changes in tension, the compressions and rarefactions that the meter would detect. Now, consider another model, derived from the Euler-Lagrange equations, where we allow the tension to vary. This more complex model not only explains the transverse waves, but also predicts and explains the variations in tension and how these two processes interact. Which model is a better representation of the actual physical system, especially given our setup with the force meter? Clearly, the Euler-Lagrange one, because it accounts for more relevant phenomena. How would the semantic view explain this difference? It would likely point to the degree of idealization. The wave equation model is more idealized, assuming constant tension. The Euler-Lagrange model is less idealized, allowing tension to vary. Both models, if we think in terms of partial structures, share some structural features with the data model derived from the experiment. But the less idealized Euler-Lagrange model shares more features, hence it's a better representation. This relies on the idea that idealization creates a kind of hierarchy or ordering among possible structures. Now, is that hypothesis true? That's debatable. But for the sake of argument, let's assume that for these theory-driven models, both the SV's mapping account and Morison's explanatory power account can handle the comparison reasonably well. The real test comes with models that aren't so directly tied to the theory. Okay, now for a different kind of beast, modeling the atomic nucleus. Back in the day, physicists tried to apply standard quantum mechanics, specifically the Schrödinger equation, to the nucleus. Problem? With multiple protons and neutrons interacting, it becomes the infamous nuclear many-body problem. No exact solutions, basically impossible to solve analytically. So, what did they do? They threw up their hands and started building phenomenological models. They crafted specific Hamiltonians, mathematical descriptions of energy based on empirical observations and educated guesses. This led to models like the liquid drop model, treating the nucleus like a drop of liquid, focusing on collective motion. Then came the shell model, imagining nucleons moving independently in an average potential, like electrons in an atom. Later, the unified model tried to combine both ideas. Crucially, these models weren't derived from first principles quantum theory for the nucleus. They were built from the ground up to explain observed nuclear properties. So, how does the semantic view handle these nuclear models? It hits a wall. First, remember SV's reliance on comparing a theoretical model from the overarching theory with a data model from experiments. In this case, the initial application of the theory failed, so drawing that sharp line is murky. Second, even if we could somehow define theoretical and data models here, how do we rank their representational capacity? These models focus on different aspects of the nucleus and represent it in different ways. Comparing them purely structurally is tricky. Third, and perhaps most importantly, SV tends to ignore the history of science. The liquid drop and shell models weren't just discarded when the unified model came along. They were important steps, providing insights that contributed to the unified model's development. Dismissing earlier models because they don't fit the SV's ideal structure would mean we can't properly understand why the later supposedly better models succeeded. It seems SV's purely structural approach doesn't fully capture the dynamics of how these kinds of scientific models work and improve. Now, let's bring Morrison's explanatory power criterion back into play. How does it fare with the nuclear models? Much better. Actually, each model explains certain features of the nucleus based on its core assumptions. The liquid drop model explains collective behaviors. The shell model explains individual nucleon properties. Each also explains the semi-empirical data that helped build it. When the unified model came along, it was considered superior because it explained even more known results, and crucially, provided a specific explanation for how collective motion and independent particle motion interact within the nucleus. Morrison's approach allows us to see these models as genuinely representational, even without a direct structural link to the foundational theory. It lets us compare their explanatory power and appreciate their historical development. It seems like a more robust way to understand the role of these phenomenological models. So, what's the takeaway from this comparison? Mathematical structure is undeniably important. Equations obviously satisfy certain structures. But reducing scientific models solely to these mathematical structures, especially ones neatly ordered by idealization and mapped to theories, seems too narrow. It makes us miss key ingredients in how our most successful models are actually built. Think about the nuclear models again. They heavily relied on empirical data and conceptual innovations, not just abstract theory. This structural-only view doesn't help us understand all kinds of scientific modeling, especially the phenomenological kind. It also risks undervaluing models that don't fit the neat SV criteria, like the unified nuclear model, which built upon earlier ones. By focusing only on the mathematical structure, we obscure the rich blend of theoretical principles, empirical findings, and creative leaps that give a model its unique representational power. It also cuts us off from the history of how models evolve and how scientific concepts are formed through this process. Another powerful critique comes from Nancy Cartwright. She argues forcefully that scientific theories, especially the fundamental ones, are packed with highly abstract concepts, think force functions, Hamiltonians, fields. These abstract concepts, she says, simply cannot represent what's happening in actual messy situations. How do we bridge this gap? Through bridge principles. These are rules that tell us when and how the abstract terms of the theory can be applied to concrete phenomena, often by referring to the kinds of descriptions found in scientific models. For theory application to make sense, Cartwright insists these bridge principles must be seen as part of the theory itself. However, she notes that only a few theoretical models work well with existing bridge principles. In countless other cases, scientists construct phenomenological models. These use theory, but there's no direct deductive link. The key insight is the abstract concrete distinction. Concrete concepts like red or hot have their own meaning, independent of the abstract theoretical concepts they might relate to. Therefore, models, whether built phenomenologically or using bridge principles, involve more concrete descriptions and are thus, in a sense, independent from the purely abstract theory. So, what's the strength of Cartwright's argument? One interpretation is that the semantic view might still have a role in understanding the foundational structure of scientific theories. But when it comes to applying those theories to the real world, focusing solely on that structure is misleading because it ignores the crucial abstract to concrete gap bridged by those principles. A stronger reading, however, goes further. It suggests that the structure of theories is completely irrelevant to how they represent the world. Why? Because theories, in their pure form, don't represent the world at all. Only models do, and models are detached from the theory because they are built using more concrete concepts that directly apply to particular physical systems. The theory provides the high-level framework, but the models are where the rubber meets the road in terms of representing specific pieces of reality. Alright, let's wrap up this section on models. We've seen that mathematical models are absolutely central to how science represents the world. But figuring out exactly what they are and how they work involves tackling a whole web of interconnected questions. How do they relate to the grand theories? How do they connect to the raw data from experiments? How are they actually constructed in practice? What kinds of ideas and ingredients go into building them? How do we use them to gain knowledge? How does the fact that they're often simplified or idealized affect their ability to represent reality? And ultimately, what is the nature of their representational power? Can we find answers to all these questions without resorting to overly simplistic views that either ignore the complexity of theory application or fail to account for the diversity of scientific modeling? Theory certainly sets boundaries, but it seems the relationship between theory and models is far richer and more nuanced than simple unifying accounts often suggest. For those interested in digging deeper into the philosophy of scientific models, there are some fantastic resources. The book, Models as Mediators, edited by Morgan and Morrison, is a must-read, containing a wealth of essays on the topic. If you want to explore the semantic view in more detail, look into works by DaCosta and French, or Hughes. And for understanding the crucial processes of idealization and abstraction in model building, Supp's work is foundational, though other perspectives exist in the works of French and Ladyman McMullen. And the Nowick. Happy reading. Alright, shifting focus now to another bedrock concept in science, observation. Traditionally, observation has been seen as the cornerstone of science. What sets it apart from, say, philosophy or mathematics? The conventional wisdom is pretty straightforward. The stuff we observe is given directly by nature. It's our raw data, the starting point. Of course, everyone agrees science goes beyond just listing observations. Otherwise, it'd be like natural history. But how far is too far? Empiricism is all about staying close to the data. The logical positivists in the early 20th century took this to an extreme. They argued that a statement only had meaning if it could be translated into an observation language, talk only about observable things. Statements about electrons reduce them to tracks on a photographic plate. Mental states? Translate them into observable behavior. Sounds neat, right? Well, it turned out to be incredibly difficult, if not impossible, for most scientific concepts. This failure led to a more relaxed version of the standard view. A theory just needed to entail some observation statements, not necessarily be reducible to them. As long as a theory made testable predictions, it was okay to have unobservable theoretical terms. So, under this mid-century standard view, how do we choose between two competing theories? Let's call them T1 and T2. The procedure seemed pretty clear-cut. First, you need to find an observation statement. Let's call it O, such that theory T1 predicts O, and theory T2 predicts not. Then, you go out and observe. Do you see O or not O? Whichever theory matches the observation wins. Simple, elegant, rational. This whole process assumes implicitly that there's a shared neutral language for talking about observations, a language free from the biases of either T1 or T2. Everyone can agree on what O means, regardless of which theory they currently favor. This seemingly objective basis for theory choice was a cornerstone of the scientific enterprise as understood at the time. But then came Thomas Kuhn, and everything changed. In his groundbreaking work, he launched a devastating critique of the standard view, particularly targeting the idea of theory-neutral observation. Kuhn argued that the theoretical framework you already hold determines what you perceive. He used the classic example of looking at a cloud chamber. A trained physicist, he claimed, doesn't just see droplets or needles. They literally see electron tracks. Why? Because their mind is equipped with the relevant theory. A novice lacking this background sees the raw visual stimuli, the droplets, the scale readings, and needs to interpret them perhaps with guidance to reach the conclusion about electrons. Kuhn extended this expertise shapes perception itself. If you have radically different theories, like one attributing cloud chamber tracks to fairy dust, you'd literally see something different. The implication is staggering. If perception is theory-laden, then there can be no observation that's neutral with respect to competing theories. There's no pure data upon which everyone can agree. If Kuhn is right, and different theories lead to different perceptions, then the whole foundation of the standard theory choice method crumbles. How can you find a neutral observation if TE and TR predict different things, or even if they predict the same thing but for different reasons tied to their respective frameworks? The very idea of a shared observation language becomes meaningless. The consequence is that theories become incommensurable. They operate in different conceptual worlds, making direct comparison or refutation based on shared observations problematic. This raises a profound question that dominated philosophy of science for decades. If we can't choose between theories based on neutral observations, how do we choose at all? What drives scientific progress if not rational adjudication based on evidence? Philosophers responded to Kuhn's challenge in various ways. Some took a very radical turn, embracing social constructivism. Thinkers like Latour and Wolgar argued that the idea of rational theory choice is a myth. Theories don't win because they're better supported by evidence. They win through social processes, negotiations, persuasion, and power dynamics within the scientific community. Truth isn't discovered, it's negotiated. Paul Feyerabend offered a less radical but still quite different take. He said, if theories are incommensurable, then they can't logically contradict each other. So, why choose? Just accept both. Accept multiple, incompatible theories. There's no need to force a choice between them. These responses challenge the very notion of objective, evidence-based scientific progress. But not everyone bought into Kuhn's radical claim. Jerry Fodor, for instance, pushed back hard. He conceded that experts might describe their experiences differently than novices, as Kuhn and Churchland argued. But, Fodor countered, does that mean their perception is different? Maybe not. Maybe the difference lies elsewhere. Perhaps both the physicist and the musician have the same underlying perceptual experience, but the physicist, armed with their theory, chooses to report it differently, interpreting the raw sensation according to their background knowledge. He even questioned the experimental evidence Kuhn cited, suggesting it could be explained by this reporting difference. Fodor's key point was that even if we grant that cognition influences perception, it doesn't follow that every cognitive difference affects perception. Maybe the difference between two scientists' theories is purely intellectual, a disagreement about interpretation or prediction without affecting what they actually see. It's conceivable, he argued, that scientists with wildly different theories could in fact see the same thing. Fodor bolstered his argument with a compelling piece of evidence: the persistence of perceptual illusions. Think about the Müller-Lyer illusion, those lines that look different lengths but are actually identical. We all know it's an illusion, we have that background theory, yet our perception isn't corrected. Why? Fodor argued this strongly suggests that perception is informationally encapsulated. It's somewhat shielded from higher-level cognition. Only a limited set of inputs can influence the output of our perceptual systems. This connects to his broader theory of perceptual modularity. If perception is modular, then differences in our background theories, especially those theories that are inaccessible to the perceptual module, won't affect what we see. So, even if two scientists have profoundly different theories about, say, quantum mechanics, if those differences don't feed into their basic perceptual mechanisms, they might still see the same tree, the same cloud, the same electron track. Fodor took this further. If perception is modular and encapsulated, then the body of background theory that can influence perception is fixed. Therefore, he proposed, we should define observability based on this accessible background. Only properties denoted by terms in this fixed accessible set count as observable. His bet was that red would qualify as observational under this criterion, while proton would not. The crucial point is that physics, with its talk of protons and quarks, likely doesn't belong to this accessible background. If this holds, it resurrects the possibility of a theory-neutral observation language, one based on concepts that are genuinely perceptually accessible regardless of our deeper theoretical beliefs. This seemed like a promising way to defend the empiricist tradition against Kuhn's relativism. However, Fodor's defense faces a major hurdle, famously articulated by critics like Maxwell and Churchland using the electron microscope eye argument. The problem is this: if observability is defined by what our current perceptual modules output, or what our current instruments detect, then it's inherently context-dependent. What's unobservable today might become observable tomorrow with a new telescope or microscope. Maxwell pointed this out decades ago. Churchland sharpened the objection: imagine mutants or aliens with senses far beyond ours, say naturally occurring electron microscope eyes. Could they observe things we currently cannot? If so, then the boundary of the observable is not fixed. It depends on technology or biology. For anti-realists, who need a firm line between observable and unobservable to ground their position, this context dependence is fatal. It means there might not be a class of entities we can never observe no matter what. Fodor tried to respond by talking about the scientific community. He argued that anti-realists need a guarantee that some claims are forever unobservable, regardless of who observes. This requires defining a fixed universal scientific community. But here, critics like Kukla pointed out a slippery slope. We readily accept blind scientists and sighted scientists as part of the same scientific community, right? They credit each other's reports, even though their sensory capacities differ. Why shouldn't we extend this logic? If we accept mutants who can see slightly further into the ultraviolet as part of our community, why stop there? We could imagine a continuum of beings with gradually varying senses. By rational extension, we'd eventually have to include beings with arbitrarily different senses, perhaps ones that can perceive electrons directly. If we do, then any theoretical entity could in principle be deemed observable by some member of an expanded scientific community. This collapses the very distinction between observable and unobservable that anti-realism relies on. So, where does this leave us regarding the role of observation? Both Fodor's attempt to defend a modular theory neutral perception and Van Frassen's entity-based distinction run into significant philosophical problems. The electron microscope eye argument and related concerns about drawing arbitrary boundaries for the scientific community cast serious doubt on whether we can maintain a coherent, defensible distinction between the observational and the non-observational in a way that supports strong anti-realism or resists Kuhnian relativism. The foundations seem less solid than previously thought. For those interested in exploring these debates further, the readings list provides a good starting point. Ayer's work captures the early positivist drive. Bridgman and Watson represent early attempts at reductionism. Kuhn's seminal text is essential reading, along with Gilman's critique of its psychological basis. Fodor's defense against Kuhn is detailed in his papers. Van Frassen's constructive empiricism is laid out in his key works alongside his responses to critics. Friedman's review offers a particularly sharp critique of Van Frassen, and Kukla's work explores alternative conceptions of observability. These texts delve deep into the complexities surrounding how we observe and know the world.